In Unit 3, we're going to be focusing on the atomic theory. So we're going to start off with just going over a brief history of how the atomic model actually developed. We're going to discuss the evolution of the atomic model that occurred over a long period of time through the work of many scientists. And we're only going to touch on a few of these scientists. We don't actually go through every single one that contributed in some way to this model. Students should also be able to relate experimental evidence to the different models of the atom. So one thing I like to always show students is the world map in 1540. We know what the world looks like now, but this progressed as evidence was gathered through voyages, and even eventually when we got into outer space and could actually get pictures of what the Earth looked like as well. So as more evidence is gathered, the more accurate our models become. So a couple of early theories about matter was Aristotle believed that different substances were made up of basically four items, either earth, fire, air, or water. And right around the same time, a little bit later, Democritus started thinking, well, if I can keep breaking something in half, what point will I reach when I can't break it any further? And he thought this particle would be referred to as an atom. And while we know now that he was on the right track, at the time, Greeks in the world accepted Aristotle's idea. However, about 2,000 years later, we're going to see a little bit more about how this atom was more thoroughly investigated. So a couple of things to point out is the atom is that it's the basic building block of all matter. It cannot be broken down chemically, and it's a single unit of an element. So Dalton's model, which you're going to see kind of resembles the idea that Democritus saw, is that he had four principles, and some of these are still hold true today. That all elements are composed of indivisible atoms. Atoms of the same elements are exactly alike. Atoms of different elements are different, and compounds are formed by joining atoms of two or more elements. Now, 1 and 2 we're going to see have changed since the early 1800s. However, 3 and 4 basically are true even today. Dalton's model, in terms of how we view the atom, is either referred to as a billiard ball or cannonball theory. These are ideas that atoms are spherical and of uniform density, solid. Now, in 1847, J.J. Thomson conducted an experiment with a cathode ray tube. And this basically creates a charged field. Now, what you're going to see is that the cathode ray is sent through the tube. We have a negatively charged plate and a positively charged plate. So what they saw was that the cathode ray was deflected by the negative electrode and was attracted to the positive electrode. Since opposites attract and likes repel, this means that the cathode ray contained negatively charged particles. He then discovered the negatively charged subatomic particle called the electron. So J.J. Thomson is responsible for discovering the electron and adding that to what we know as the structure of the atom. His model is referred to as the plum pudding model, which did make sense at the time because plum pudding was a pretty common food. So the positive charged substance, the pudding, was with the negatively charged electrons that were embedded and scattered about, which were considered the plums. Now, I want to relate this to the chocolate chip cookie dough, that the cookie dough is the positively charged substance that fills the atom, and the chocolate chips are the negatively charged electrons embedded into the cookie dough or into the positively charged substance. So in this idea, we have still a semi kind of jelly-like atom that have these embedded electrons into it. So again, overall, it's neutral, which is still true today, but again, a little bit different, not a solid sphere. There's some different densities because of those negatively charged electrons. Now, Rutherford had the gold foil experiment. This is huge. I would highlight this in your notes. This is something you absolutely have to know all about in 1908. He fired a stream of tiny positively charged particles, which are called alpha particles, at a thin sheet of gold foil. Now, most of the particles passed through, but some were deflected at different angles. So this gave him two pieces of information. First, again, most of them passed through. These are the non-deflected particles that passed through, which meant that they weren't hitting anything. And then a couple, or some, I should say, of the particles were deflected. That means that they were hitting something fairly solid or dense. So this led to his model, which is that the atom is mostly empty space that came from the alpha particles that were passing through, and that there was a small, dense, positively charged center called the nucleus. That was where those alpha particles were deflecting off of. And then he was able to summarize that the negatively charged particles must be outside the nucleus, because the fact that the nucleus was going to be positive because of that deflection of those positive alpha particles. So this is a general idea of what Rutherford's model would have resembled, with a dense positively charged nucleus and those negatively charged particles on the outside of it. Now, there were some problems with Rutherford's model. The model was unstable, and it could not explain the atomic spectra or light that scientists observed. And we're going to talk more about this in a later concept. So a spectrum line, just for right now, all you need to know is that it's produced when an electron falls from a high to a low energy level, which emits light. So the electron absorbs energy, it jumps up a certain number of energy levels. When it falls back down, it gives us a very specific amount of energy in a form of a very specific color of light. So the Bohr model, they were able to say that there were specific electron levels or path around the nucleus that these electrons were jumping to and from. So this was referred to as the planetary model. In middle school, you drew a lot of these Bohr diagrams. Now, progressing a little bit further is the wave mechanical model, or the modern model. Now, a lot of ideas and theories contributed to this, but we'll basically sum it up in the fact that electrons do not move around an atom in specific paths like planets around the sun. We say that they have distinct amount of energy, and they move in areas called orbitals. This is a key vocabulary term. Again, I would highlight or star the term orbitals. An orbital is an area of high probability for finding an electron. One big part that was contributed to this theory was that it was based on the idea that electrons exhibit both particle and wave-like properties. Now, we can find the particle's position, but you can't say where a wave starts and ends. So it's kind of this combination of what they think electrons act like. So the wave mechanical model is sometimes called the electron cloud model because of that idea that the darker the cloud is in our pictures, the higher the probability of finding that electron. We'll see later on that electron clouds are not just circles. They take on various shapes depending on the size or type of orbital that they are. Okay, so just make sure you go back and review Dalton, Thomson, Rutherford, Bohr, and then the wave mechanical model.